Chapter 2, Lesson 1, Pre-Calculus. We are going to look at linear functions, and again we've used linear functions since way back in Algebra 1 and probably even before. So we'll run through these pretty quickly, the different forms, and do a little application. So linear functions are first degree polynomials. The highest degree of the exponent or the highest exponent of any term in the equation is a 1. Linear functions are slanted lines. Neither vertical nor horizontals are actually polynomial functions. And let's take a look at why you think that is after we cover this. F of x is equal to ax plus b. That's what you'll see on your calculator when you do linear regressions, or mx plus b. It's the same thing. A here is the slope. And remember, we talked about in the last chapter about vertical stretches always showing up as the letter A. Well, this A here is a vertical stretch of the slope. A number bigger than 1 makes the slope slanted. That rise gets bigger while the run stays at 1. A fraction, the run gets bigger while the rise stays at 1. So A, again, is a vertical stretch. So we're using this form because we're talking, or we want to look at these in terms of vertical stretches and vertical shrinks. But basically, it's the slope. It's the same thing. You would calculate it the same way. And actually, we'll talk about that calculus connection in just a little bit. Now, vertical lines are not functions. Do you know why? I'm not going to answer that question. I want you to answer that question. Why are vertical lines not functions? And horizontal lines are graphs of constant functions. You think of the function y equals x, or 5, excuse me. F of x is equal to 5. That's a horizontal line at 5, so that's a constant function. So technically, it's not a linear function. So linear functions, by technical definitions, are only lines that are slanted, that are neither vertical nor horizontal. And again, I would like you to discuss in your summary why vertical lines are not functions, and then horizontal lines are actually constant functions that have a degree of 0. All right. Now, some things to remember that you've looked at before. Slope-intercept form is y equals mx plus b. Point-slope form, y equals y1, y sub 1, or not equals, y minus y sub 1 is equal to m times the quantity x minus x1, x sub 1. M is the slope, which you calculate using y2 minus y1 over x2 minus x1. The x and the y1 here are an ordered pair coordinates. So you take the coordinates of any point and you put the x value here, the y value here, you inject substitute your slope here, and you have your point slope form. Now, when you want to go to slope-intercept form, you can rarely start here. You'll want to start in point-slope form in most of your equations, and then solving that point-slope equation for y will give you slope-intercept form. So the calculus connection is this. Rate of change means slope, and the rate of change is a comparison of two things. Two things are changing. So what's the ratio of their changes? Now, when we're talking about slope, we're looking at a vertical change up and down. So how big a change do we have? Well, you take the y-coordinate of one and subtract the y-coordinate of the other. That gives you the distance between the two. So that gives you the vertical change. The x2 minus x1 is you're taking the x-coordinate of one, subtracting the x-coordinate of the other. That gives you the distance between the 2 points, giving you the horizontal change. So slope is just simply a comparing of what's the vertical change compared to the horizontal change. Okay? Now, the y values we've been talking about, we're using this function notation f of x. Well, if we use this function notation then in our slope formula, if you take any 2 points on the graph, A and B, so that means you have 2 points on the graph. The x-coordinate of one is, let's say, A, and the x-coordinate of the other is, let's say, B, then what's the y value? Well, the y value is going to be what you get when you plug A into the function, or f of A. The y value for this coordinate is going to be the y value that you get when you substitute B into the function, so or f of b. So if we use this notation then, where this is an x-coordinate and this is its y value, this is a x-coordinate and this is a y value, and we substitute these into our formula, we actually get this rate of change, which is the f of b, or the y value of the I'll get it. The y value when you substitute in b minus the y value when you substitute in a. So this is actually y2 minus y1 over x2 minus x1. We're just using these two values because when we get to calculus, we're going to look at an interval. Let's say this x-coordinate a all the way over to this x-coordinate b, and what's this y value? Well, that's going to be f of a. And what's this y value going to be? Well, that's going to be f of b, and so we're going to be looking at this interval right here when we get to calculus. So we want to be able to calculate what's going on here, and actually we're just using function notation when we get there. So this really isn't any more than doing the rate of change as m, which is the rise over the run, which is change in y over change in x. And if you've had physics, you've probably seen this change in this delta symbol. This is the Greek symbol delta, which represents change. The change in y over the change in x. So that's all it is. So the initial value then, what we want to talk about is the beginning value is for a function f is usually f of 0 when you substitute in 0 into the function. Because again, if we think about a graph on a function here, when we're relating it to a real world problem, time usually starts here at 0 or whatever we're talking about on the x-axis. So when no time has gone by, what's the y value right here? Or mathematically speaking, what's the x-coordinate here? 0. So what is this y-coordinate? F of 0. So at the initial point 0, where you're starting in most cases when we're talking about applicational, 0, and then the y value that you get when you substitute in 0, that's actually the initial value or the y-intercept. Now when we're looking at a polynomial function and we have the equation in standard form, the constant term becomes the initial value. Because if you think about it, if you have multiple terms, let's just say x squared plus 2x plus 3, let's even put an x cubed out here, let's even put a 4x to the 4th. What's the initial value? Well, the initial value is going to be what I get when I substitute in 0. Well, if I put in 0 for all these x's, what are all these terms going to be? 0, leaving me only the constant here at the end. So when you're talking about a polynomial function, this value out here becomes the y-intercept. And again, if we were to do y equals mx plus b, this is the y-intercept. We know that because we talked about that before, y-intercept. Well, why is it the y-intercept? Well, actually, because if I substitute in 0 for x here, so my x value is 0, what is this going to simplify? It's going to simplify to b, so it makes sense that that's my y-intercept. Okay, so a lot of connections to what we've been doing in the past. I'm going to go ahead and take a quick video break, and I'll come back and I'll do these types of examples in the next video. It'll be a short video, and I'll show you how you write the equation or match the linear equation that satisfies these conditions.